Sorry. Okay. So as I presented in previous sessions, so we have the Cloud Firmware solutions and openBMC solutions. We have Cloud Firmware solutions. So as discussed in the community, people are quite interested in how we design a RAS feature of RAS enablement on the Cloud Firmware solutions. So here I like the quick update or introduce our solutions. How could we do it on the RAS related? Yeah, with the current new firmware solution. So the niche is Intel fellow, but she will not be here today. So I will present for these sessions. Yeah. As previous sessions said, this is the general. We listed for the host firmware solutions. We have a separate firmware as a host firmware as 3 parts. Silicon support module. So bootloader, we have we can have the Tiano, coreboot, slimboot. We have payload, EDK tool input, and there we have the OS shake off. So this is a very general update here. So here we focus on the FSP because this is what we have done on the Intel platform. So we were very appreciate Intel have collaboration with the Bytedance for this collaboration. So we were focused on the FSP coreboot input solutions with the RAS implementation. So what's the RAS? So here I list some areas for the system RAS. The first one is we have the system SoC or IP feature RAS features. So this is for the hardware level. So this the RAS features have been designed in a system in a SoC IP. For example, such as the memory ECC. So this is have been designed in a memory controller, such as the PCIe hot plug. This is designed from the PCIe IP, such as Poison, maybe related with the core and the mesh kind of IPs. So then the SoC can integrate them together. So all these features, the first layer have been implemented by the hardware level. Another one is in the boot time. So we should initial these features. RAS features. So this is from boot level. Definitely, these features should be init by the firmware. But based on the current experience, maybe we don't need to put everything in it by the host firmware. Maybe we can, because every process have the management process right now. So some of them are transparent to the users. Maybe some feature can be init by the transparent firmware, or we also can do to init by the host firmwares. Yeah, of course, we should do the firmware side. Another one is error reporting. So error reporting is very important in data center. So hardware detect and then how to report these errors. So we usually have define some error domains in the SoC. So on the x86 platforms, there are machine check architectures. So we can define the error domain for each IP, each actions, each operations. Another one, we have the in-band and two-band error reporting method. Yeah, so for in-band, it can report error to the OS operating systems. For out-of-band, it report error to the BMCs. We have different scenarios. So based on my experiences right now, most of the CSP for cloud service providers, they are quite interested in the error reporting to the BMC because because they have the bare metal kind of the business model. So they don't want the customer can get any information about the hardware errors. Yet, but for some internal mobility only for the internal use, so these cloud users, they're still quite interested in get some error information from the in-band. Then they can collect all the lots of the mass error data. They can do analysis. They can do the analysis. Yes. So for the Bytedance, because we have some systems we have a cloud service for the customers, but we have most of our business for our internal users. So we are quite interested. We get the error data from in-band. That's quite because we maybe on the Intel x86 platforms we have the MCA logs, and there we can get every error information from the in-band directly. So we have the mass systems. I will introduce later in the next page. So this is for error important. So error reporting is, in my opinion, is very important. Is the key, quite important in our data center. The last one is the error handler or recovery. This is for the run. Is also the runtime phase. So for the first one is for the hardware error recovery. We have the retrieve. If we have the error with the retrieve, it's from the hardware design or IP level. We have the correctable ECC, CRC. This is also the hardware level. If we have the mirror feature support, we can recover the data by the mirror kind of features. So these are from the hardware level. Another one, we have the software error handlers. For example, for the SPPR, ADDC, hop-lock kind of things. So this is from the OS or firmware level. We can do kind of the recovery. These are from the software error handlers. The last one we have software error is like a MC recovery or data poison. So we should have the action for the OS level. So OS will do coordinate with the hardware such as the page offline, and then the error data will not be accessed in the future anymore. Yeah. So with this case, we can see which one is necessary. For first one, so the error RAS feature init is necessary. We need to do in our firmware. So in-band error reporting, auto-band reporting, I don't think it's, maybe it's optional for the firmware. I will introduce in next page. For the error handlers, for SPPR runtime SPPR is quite useful, but this is the new feature in this generation. But for ADDC, because it needs the SMI, need the application processors to interrupt, to handle some RAS features. So currently in the CSPs, we don't interested in AP to handle the error other features. So we have not implemented this one. For hop-lock, we can directly move to the OS to join it directly. So we don't need the firmware to implement implementation for the hop-lock. For other software recoveries, both of the operation system and operation system need to do. We don't have a relationship with the host firmware. Yeah. So here is the page we have built in our data center. We call CSP hardware error reporting. So we have in left side we have each hardware module. We have CPU, motherboard, DIMM, NIC, SSD, GPU. This is each device, and then in the machine check architecture, so we have each MCI banks. So we have core MCI banks for the CPU cores. We have on-core MCI banks. We have on-core MCI banks for some mesh kind of things, PCU kind of things. We have DDR for the DDRs, for the PCIEs, for the PCIEs. We have the DDR CSRs for more error information for the DIMMs. We have PCIe ARs for more error information for the PIs. So when any error happened in each device or modules, all these errors will be recorded in these MCI banks. Then these MCI banks we call the error domain. Yeah, and then this error domain we can report to the OS system by the in-band from the EDEC or MC log, and also this error domain can report to the BMC by auto-band packet. So here is our, and we don't have any SMI or API in the interrupt on the application processors. And after we got lots of data from in-band, so we have two purposes. The first one is we do the data analysis, and we are going to share this data back to the system vendor and the silicon vendor. Tell them these are errors we happen to meet in our data center. You can improve your design in the future. Another one is we also analyze the data. We put back to our operation and maintenance team. Then we do our operation maintenance team. Yeah, this is our solution we designed. Another one is. Here is our HSR solutions. We call hyperscaler error reporting solutions. So from the left side, we have online systems. We build the in-band and auto-band. So from OS side in-band, BMC side is auto-band. From in-band, we have the EDEC. we have MC log. So all the data were collected and then to the engine. The engine will send the data to the database. So the first one is a raw data database. For autobahn, we have another BACD. BACD is developed based on the Intel ACD, automatic crash dump. So we have put more additional error informations in the autobahn in the BMC side, and they all data have stored in our raw data database, and we have one specific error decoder in our infrastructure, and then we decode the whole data in our database. So then we can know any system, which IP, which time slot, which errors, which operations, which MCS MS COD, all the information we can get. And these data we can have two purposes. As I said, the first one we send to these data for the data analysis, and then we send this data put back to the system design and the SoC design. Another one is this data we will also put to our operation and maintenance team. Another one is for the data poison. So when we analysis, it's for example, for the memory errors, where we get the restricted data on the memory from the memory corrected error. So we have a judgment or evaluate system if it's going to have an uncorrected error in a few times later. So we have notified the online system to the MSA recovery on one specific system address. Yeah, this we also build in our systems. So these systems we focus on the error reporting. There we also can support some recovery in the system level. But you can see this system. Go back to this system. So we don't have for the firmware side, for host firmware side, we only do the RAS feature initiative. For the runtime, we don't want the host firmware join any RAS activity. Yeah, that's our purpose. Because customer or business people, they don't want the impact by any errors. Yeah, but as I talked with a lot of people, so for bare metal case, they're not interested in the error from the in-band, but they would like to put all the error data from auto-band. That should be fine. Yeah. But for our system, for our internal business systems, the BACD is focused on the crash for the fatal error, the system crash. But most error we can handle in the in-band. Yeah. Here is the implementation from BMC side. So this RAS offload is very popular. We prefer it in the Cloud Firmware. So we don't want the much SMI usage because we don't like the performance impact caused by the RAS event. Another one we would like the FSP or just the firmware, host firmware very simply. And last one is we like the multiple business management systems. Sustaining for systems is separate in our infrastructure, don't relate it with the online systems. So currently the industry trend is to move to the in-band RAS handlers from the execution core to others. Others means BMCs or other management cores. So you look at the some SoC design. So there are some many management core design, but on the x86, so we prefer to move this part to the BMC. Yeah, this as well. Yeah. So we can do the error dump to a BMC for error analysis to a BMC. Yeah, that's what we prefer to do right now. We don't want any application processors to do more things for the error handlers. Yeah, that's our purpose. Oh, quite quickly. That's the last page, call to action. So we build on the Cloud Firmware system that we build the RAS reporting system in our data center. We trying to separate the RAS actions in the host firmware. So we try to build the auto-band solutions, or try to build the in-band solutions. So we like to separate the RAS related with the host firmware. That's the host firmware can pretty easy. Yeah. That's all for me. Any questions? Another one we're trying to share. So after we build these systems, we can get any CPU, any DIMM, and PCI cards, the error data in our data center. So we have some volume mass data. That's very useful, yeah. Any question? Okay, Nill, please.
This discussion about RAS is related to open platform firmware. Can you clarify the connection?
Okay, actually this system we have discussed in the hardware fault management, right? You know that?
Yeah, I mean, this presentation was done last year also.
Yes, most of the content have been last year. Yeah, but in the open system firmware community, people are quite interested in how we could implement the RAS in the firmware side. Because right now in the x86 systems, most of the RAS features have been implemented by the host firmware. They have lots of SMI kind of stuffs. So people are quite interested in how we can handle the RAS in the new firmware solutions. Yeah, I'd like to share here one more time. Yeah.
I see. So some of the solution you're sharing here is firmware based then? Which firmware?
Actually, we don't like the firmware base.
I know. That's why I'm curious why this topic is discussed here.
Yeah, I just share the people this solution.
Okay.
How we do the RAS solution on the new firmware.
Without firmware.
Yes.
But presenting in firmware.
Yeah.
Thank you.
Thanks, Anya.
Hey, I have a question. So you talk about a lot on error log inside the logging correctable errors, uncorrectable errors, and crash dumps. My question is, that's for this plot, like when you do the operation the maintenance, for example, if you want to do post-package repair or do ADDC and other operations, how does this, where does the decision be made of which RAS action is going to be taken, and what is the feedback loop to drive those actions?
For the soft PPR or for
for post-package repair or for ADDC, how do you drive the RAS feature?
Very good question. For the post-package repair, right now so far we only implemented the hardware post-package repair. So the system after system reboot, we will have these features. So where we have the error data in our infrastructures, so we have record to this system. We will do a judgment. If this system we are trying to do the hardware PPR, so we will send some information to the online systems. For next boot, the system will try and do the hardware PPR and then do the test. After the test pass, it's okay. If the test failed, so you report to the operation and maintenance system. Yeah.
So basically, your decision logic is a kind of service, and then you feed it back to the machine.
Yeah, it's all offline, so we can do to change the policy anytime. Yeah, all these policies are offline. We don't need to put the firmware because the firmware update is hard work. It takes long efforts. So we like to put the offline for some infrastructure systems, so we can change the policy to do the update directly. Yeah.
Thank you.
You're welcome. Thank you.